Okay, so let's do one more example with just linear, and we'll do it with 3 factors. Okay. And in this case, we'll look at both methods. So let's take a third case. Okay. Let's say that we have 2x plus 1 over x plus 3, x minus 1, x minus 2. So I'm already factoring the denominator for you, just because I don't want to be factoring cubics right now. Okay. And this is a proper fraction. The degree of the numerator is less than the degree of the denominator. Let's even make this 2x squared plus 1, just so that you see what happens when we have something that's squared. Okay. So in this one, we have 3 factors. So 3 factors means 3 denominators. So we're going to have a denominator with x plus 3. We're going to have a denominator with x minus 1. And we're going to have a denominator with x minus 2. Every one of these is linear. So each one gets an A, a B, and a C. So notice we just move through the alphabet. So here we could skip the first step. We didn't have to factor. It was already factored. So now we multiply everything by the denominator on the left. And I'm going to write it like this, because it doesn't really matter. X plus 3, x minus 1, x minus 2. That means that this is going to cancel. That's the whole point. Okay, so here's the difference. This is going to give us 2x squared plus 1 is equal to A. And this time, not more cancels. Not everything cancels. It's not as simple, right? We're left with an x minus 1 and an x minus 2. The x plus 3 canceled, but we still have 2 factors left. Then we have the b. Now with the b, we're left with x plus 3, and we're left with x minus 2. The x minus 1 canceled. And with the c, hopefully you could pause the tape and you could see what is canceling. You can write it out. But with c, the x minus 2 cancels. So we're going to do this using both methods, and we're going to see if this, that way you see the difference between the 2 methods. And in this case, the first method is still much easier, but the first method isn't always going to work. So you'll see here it works, but when we do quadratics, it's not. Okay. So here, again, we want to figure out what is an x value that we could plug in that's going to get rid of either A and B, B and C, or A and C. So let's start by trying to get rid of B and C. So remember, anything that's multiplied by 0 is 0. So if we could make either x plus 3 or x minus 2 equal to 0, then this whole thing is 0. So let's just write that. If x plus 3 equals 0, or x minus 2 equals 0, so or, doesn't have to be both, then this whole thing equals 0. Okay, and that's important because we know that there's one of 2 things that we could plug in that's going to make that true. We could either plug in -3, and then we have b times 0 times some number, which is 0. Or we could plug in 2, Now we want to eliminate B, but we also want to eliminate C. So for here, we could plug in -3 or 2. For here, we could plug in -3 or 1, so there's an overlap. If we plug in -3, we get rid of both B and C, okay? So get rid of both B and C, and we could solve for A. Let's figure out the other numbers that we can plug in. So this allows us to solve for A. Let's see what would allow us to solve for B. So in this one, we would have to have a number that makes both A and C equal to 0. So here, if you notice, they both have x minus 1 in common. So if we plug in x equals 1, then we get a 0 here, which makes this whole term 0. And we get a 0 here, which makes this whole term 0. So what we get here is if we plug in 1, we get rid of A and C, so we can solve for B. So that we could solve for C. So again, we're looking for something that they both have in common. They both have an x minus 2 in common. So if we plug in x equals 2, then we get a 0 here, which makes this whole term 0. And we get a 0 here, which makes this whole term 0. So we're just left with this. So this is our last one. So if we plug in 2, we get rid of A and B. So we can solve for C. Okay, so let's start this. Let's do each one. Let's start with -3. So 2 times -3 squared plus 1 equals A times -3 minus 1, -3 minus 2, plus B, -3 plus 3, -3 minus 2, plus C, -3 plus 3, -3 minus 1. So this gives us 2 times -3 squared is 2 times 9. So that's 18. So I'll put this in as separate. Okay. 18 plus 1. Then we get A. -3 minus 1 is -4. -3 minus 2 is -5. And then we get plus B times 0. You don't even have to calculate this, but I'll put it in. Plus C times 0. This goes away, this goes away. So we get 19 is equal to 20A. And we could divide both sides by 20. And we get that A is equal to 19 over 20. notice we get a fraction. I'll show you how to deal with that when you plug it back in. But it's not a big deal that we get a fraction. This doesn't make it any harder. What you'll notice is we will start doing this. We won't do the whole thing with the second method, but we'll start doing it so that you can kind of see what happens when you use that second method. It doesn't make it impossible to solve it. It just makes it longer, much longer. Okay, let's plug in x equals 1. So we have 2 times 1 squared plus 1 is equal to a times 1 minus 1 times 1 minus 2 plus b 1 plus 3 1 minus 2 plus c 1 plus 3 1 minus 1. And again, I'm going to put in this extra step. You may automatically say, okay, the A and the C go away. We don't have to do that extra step. I'm doing it here just so that you see it more clearly, okay? So we get 1 squared is 1, so times 2 is 2. So we get 2 plus 1 is equal to A times 0, which should happen. You should always double check for that. Times negative 1 plus B times 4 times negative 1 plus c times 4 times 0. So 2 plus 1 is 3. This goes away, and this goes away because they're being multiplied by 0. And then 4 times negative 1 is negative 4. So we get negative 4b. And we're going to divide both sides by negative 4. So we get that b is equal to negative 3 over 4. And yes, these are a lot of work. It does take time to solve these partial fraction decompositions. It's not a short process, but it's not a difficult process either, right? All of these things, we haven't done anything that's particularly difficult. And then finally we said if we plug in 2, we'll be able to solve for c. So let's plug in x equals 2. So now we have 2 times 2 squared. So remember, order of operations, when we solve this, we do the 2 squared first. Plus 1 equals a times 2 minus 1 times 2 minus 2 plus b. You can skip some of these steps, do not skip them all. Times 2 minus 2 plus c times 2 plus 3 times 2 minus 1. So 2 squared is 4. So 2 squared times 2 is 8. So we have 8 plus 1 here equals a times 1 times 0. So again, you don't have to do this step because you know you don't have to do this calculation because you already know that you're canceling out the a. But you should double check. You should always double check that you're going to wind up with the 0. And then plus b. And 2 plus 3 is 5. 2 minus 2 is 0. And then finally c. 2 plus 3 is 5. 2 minus 1 is 1. This term goes away. This term goes away. And we're left with 9 is equal to 5c. So then we divide both sides by 5. And we get that c is equal to 9 over 5. So now it's just a matter of plugging back in. So let's go back to the original. We had 2x squared plus 1 over x plus 3, x minus 1, x minus 2. And then we had a over x plus 3. So a is equal to 19 over 20. 20. So here's how you would plug it in. The 19 is in the numerator, and the 20 just goes into the denominator. So it would look like this, okay? Because essentially what you're doing, if we go back here, essentially what we're doing is we're doing a times 1 over x plus 3. So if a is 19 over 20, we multiply the numerator and we multiply the denominator. So 19 times 1 is 19. And then we have our 20 times x plus 3. Okay, so our denominator, when we have a fraction, our denominator of a is just going to go into the denominator of our rational expression here. And then that would be true for all of them. So that means that b was negative 3 over 4, so I'm actually going to write it this way now with a minus. It's negative, so we're just going to change this to a minus. The 3 goes in the numerator. The 4 goes in the denominator with the x minus 1. And then we have c is 9 over 5. So that's positive. The 9 goes in the numerator. And the 5 goes in the denominator with the x minus 2. And that would be our final answer here. Now, I want to start method 2. Okay, method 2 is far more algebra heavy, but I want you to just get an idea as to how it works. We're not going to use method 2. We're not going to finish it, okay? We're just going to get it to the point where we have the coefficients, the corresponding coefficients equal to each other, okay? Just so that you get accustomed to this. So let's put this in a different color. We're going to do method 2. Same problem. So we had 2x squared plus 1 is equal to a times x minus 1 times x minus 2 plus b times x plus 3 times x minus 2 plus c times x plus 3 times x minus 1. So this is a far more algebraic heavy, as I said. There's a lot more algebra here because our first step is to multiply all of this out, okay? So here it's not just distributing the a to one thing, it's taking the x minus 1 and x minus 2, multiplying it, and then distributing the a. Taking x plus 3 times x minus 2, multiplying it, and then distributing the b. X plus 3 times x minus 1, multiply, and then distribute the c. So it's extra work here because you're doing a lot more multiplication. So let's actually do that. So you get 2x squared plus 1. Do this in 2 steps. I would recommend it. So x minus 1 times x minus 2 gives us x squared minus 3x plus 2 times a. Then x plus 3 times x plus 2 times x minus 2 gives us x squared plus x minus 6. And then we have plus c, and we have x plus 3 times x minus 1, which gives us x squared plus 2x minus 3. Okay, so we multiplied all of our quadratics first, and then we're going to distribute our constants. So we have ax squared minus 3ax. So notice I put the 3 first. There's not any specific reason for that other than it looks nicer. Plus 2a. Then we distribute the b. So we have bx squared plus bx minus 6a. And then finally plus minus 6b, sorry. Plus cx squared plus 2cx minus 3c. So we distributed the constants here. So first we multiply. Multiplied each of these factors together. And then we distributed the constants. Now we're going to rearrange. So like terms are together. So that means all of the x squares are together, all of the x's are together, and all of the constants are together. So it's going to look like this. The ax squared plus bx squared plus cx squared. Then we have negative 3ax. We have a plus bx. And we have a plus 2cx. And then we have our constants. So our constants are 2a minus 6b minus 3c. And we're just going to group these together and factor. So we're going to factor out x squared. Then we're going to group these together and factor out x. These have no power of x, so these are just our constants. So what we have here is 2x squared plus 1 is equal to, we're going to put the x squared in back, a plus b plus c times x squared. Then we have plus negative 3a plus b plus 2c times x. And then the last part, we're just going to put it in parentheses so that we know it's together. Well, now we're going to equate our coefficients on the left with our coefficients on the right. So keep in mind that this 2x squared plus 1 is in standard form. This is 2x squared plus 0x plus 1. So that means that our coefficient of x squared on the left is 2. So that's going to be the coefficient of x squared on the right. The coefficient of x on the left is 0. There was no x, so the coefficient is 0. So that's going to be the coefficient of x on the right. The constant on the left is 1, so the constant on the right is 1. So we can set up a system of equations, and you'll see why we don't like it, where we say a plus b plus c is equal to 2, because that's the coefficient of x squared. Negative 3a plus b plus 2c is equal to 0. And 2a minus 6b minus 3c is equal to 1. And we have to solve this system. So we've never actually done a linear system of equations with 3 equations. Essentially what you would be doing is you can use elimination, okay? You would try and solve 2 at a time, where you figure out, okay, here's what b plus c is. You can use elimination, but I would probably recommend substitution, where you substitute in what a is. So a is 2 minus b minus c. You could plug that in here. And then from here, you can combine like terms and use elimination, okay, substituting in into both of these. Or you can use substitution again. Okay, so it's a much more complicated thing. I don't want to spend a lot of time on solving a system of 3 equations. I just want you to see that you can do it. You can absolutely do it. It's just a lot more time consuming. Substitution is probably the easiest way. So we're not going to do that, but you absolutely can. So this is a case where it's so much easier to do it using the first method. Okay, let's take some examples where we have something quadratic. Okay, we're not necessarily going to go through and do an extensive solution. We're going to try and keep it simple, and then we'll take a quick look at the process for improper fractions. But we're not going to do any improper fractions. So let's take one example. Sorry, I'm just looking at my sheet to... Okay, let's do the example of, that was number 2 or number 3? That was number 3, so number 4. And in most of these, if it's linear, okay, with linear factors, I will ask you to solve for the constants. In some cases, I won't, okay? And if I say don't solve for the constants, essentially what we want is this. If we say do not solve for the constants, you would stop here. You wouldn't do any of this extra work, okay? Okay, let's take a fourth one where we have quadratic factors, just so that you see how it works. So let's say that we have 3x squared plus 4x plus 4. And we're going to divide this by x cubed plus 4x. Okay, so we're going to solve this one all the way through. We're going to solve this using the second method, okay? And then for everything after that, we're not solving for constants, okay? So after this is going to go much, much faster. So first thing that we do is we factor. So we have 3x squared plus 4x plus 4. And if we factor, we wind up with x times x squared plus 4. So we were able to factor out an x. X is in common for both of these terms. And because we can factor out an x, we have x times x squared plus 4, but x squared plus 4 is not factorable. Right? This is a sum of squares, it's not a difference. So we can't factor this any further. So we have two fractions, so I'll rewrite this here. 3x squared plus 4x plus 4 over x times x squared plus 4. And here we have two fractions because we have two factors here. First one gets an x, second one gets an x squared plus 4. Okay. This is linear. This x is linear, this first one. So it gets a constant. Now we said when it's quadratic, it gets, the numerator is in the form ax plus b. So we already used a, so we're gonna write it as bx plus c. Okay, so this is quadratic. So the numerator is not a constant, it's linear. It's linear. Okay. Which kind of makes sense, right? In order for, so first of all, we need it to be less than x squared, right? We need these to all be proper fractions. They always have to be proper. So the degree of the numerator has to be less than the degree of the denominator. And we need to somehow wind up with an x cubed in the denominator. So we have to, this has to be, the degree has to be 1 less than the degree here. Okay. So the only way that's going to happen is if we have an x here. Okay, if this were linear, there would be no way for us to wind up with an x squared up here. Okay, so we know that we multiply both sides. So I'm going to notice I put parentheses around the whole thing. So when I do that, I'm saying you're multiplying everything in the equation. So we've done that before. You've seen that before. This is going to cancel. And what we wind up with is 3x squared plus 4x plus 4 is equal to a times x squared plus 4 plus bx plus c times x. So we're going to do this using the second method, okay? If we plug in 0, by the way, we can eliminate the b and the c and solve for a, okay? And if we plug in 2, but there would be no way to eliminate the a and the b to just be left with c. So we can, in other words, we can solve for a by using the first method, but we can't solve for b and c by using the first method. So that's why we're just going to use the second method, okay? Hopefully that was clear. We could get rid of the b and the c so that we could solve for a, because we can just make x 0. And then we have 0 times bx plus c, and we're left with just a. But there's no way to get rid of, let's say, the a and the b so that we can just have c left over. That can't happen, okay? So that's why we're using the second method. So we're going to distribute. So we distribute the x, and we distribute the a, and fortunately we're not multiplying any quadratics, so this is an easy distribution. So now we have 3x squared plus 4x plus 4 is equal to ax squared plus 4a plus bx squared plus cx. Now we can rearrange, okay? We want to rearrange it so our exponents are going down, and so that we combine like terms. So the a and the b are going to be grouped together. So we have 3x squared plus 4x plus 4. We have an ax squared and a bx squared. Then we only have a cx, and we only have a 4a. So the only thing that we have to do is we have to factor out the x squared from these first two terms, okay? Because we already have just a cx and just a 4a. There are no other x's, so we don't have to factor out an x anymore. So that's going to give us 3x squared plus 4x plus 4 is equal to a plus b times x squared plus cx plus 4a. So now we're ready to, we call it equating the coefficients. So a plus b is equal to 3. C had already solved for us. C is equal to 4. And 4a is equal to 4. So a plus b is equal to 3. The coefficient of x squared is the same on the left and the right. The coefficient of x is the same on the left and the right. So notice we already have c. The constant is the same on the left and the right. So we can use this. This isn't even a system. We can use this to solve. So if 4a equals 4, then a is equal to 1. So we have c, we have a, and now we need to solve for b. So a is equal to 1, so 1 plus b is equal to 3, so b is equal to 2. So this is a really, really fast solve, okay? So even though we used that second method, this was so fast, and it was faster than plugging in x equals 0, solving for a, and then having to do this anyway, okay? The only time that could be helpful is like in the last problem where you had a really complicated system. then it can be helpful to do something like that. So what we have here then is we could write out our final answer, 3x squared plus 4x plus 4 over x cubed plus 4x. And this is equal to a, which is 1, over x, plus, and then bx plus c. So b is 2, and c is 4, over x squared plus 4. Okay? And that's how you solve for the constants. So in the future ones, let's not solve for the constants. Okay? So we're not solving for the constants anymore. We're just doing denominators. So we're just going to take a bunch of examples, and we're just going to go through how you go about doing it, and this is not super complicated, okay? We're just going to go through a bunch, just so that you get accustomed to working with the denominators, and then you could use all of these as examples of how to solve for the constants. So let's say, for example, we had 3x plus 8 over x minus 4, x plus 2, x squared plus 1. Okay, and then let's even add in, since we're not worrying about solving for the constants, x squared minus 3x plus 3. Okay, so first of all, x squared plus 1 and x squared minus 3x plus 3 are not factorables, so we don't have to worry about that. And if I'm telling you not to solve for the constants, you should still make sure that you don't have things that are factorable. So we have 4 fractions here because we have 4 factors. So we have 3x plus 8. So the first denominator is going to be x minus 4. Again, the order doesn't really matter because you're adding, but we may as well do it in the order it was given to us. X plus 2, then we have x squared plus 1, and we have x squared minus 3x plus 3. So you should be seeing if you could fill in the tops. Okay. X minus 4 is linear, so its numerator has to be constant. X plus 2 is linear. Numerator must be constant. X squared plus 1 is quadratic, so the numerator is linear. So we already used a and b, so we're going to use cx plus d. And x squared minus 3x plus 3, it's quadratic. Numerator is linear. We already used the other letters, so we're going to start at e. So it's ex plus f. And that's it. We're not going to go any further. And by the way, if when you solve, you get something with x cubed on the right, but it doesn't exist on the left, you would just say that that's equal to 0. So, for example, if there were no 3x squared here, but you have an x squared over here, you would have just said, okay, a plus b is equal to 0. Okay, so even though it doesn't exist, and even though it wouldn't be part of standard form, if it's on the right, then on the left, you just make it equal to 0. Okay, let's take one other type of instance before we talk about improper fractions. The other type of instance is if you have something that's linear, but think of it as like a multiple, as a multiplicity greater. So if we have something, a factor that has multiplicity greater than 1, then it works a little bit differently. Okay, so let's take an example. Let's say that we have, I'm going to keep these numerators simple because it really doesn't matter. 6x squared minus 7x plus 2. Our numerators are irrelevant because we're not solving for constants right now. Let's say that we have an x plus 1 squared, okay, Well, this is really, okay, this is really a factor that has a multiplicity of 2. So we're going to have 2 fractions, but it works a little bit differently. One of them is going to have an x plus 1, and the other one is going to have an x plus 1 squared. Okay? Now this kind of makes sense. Think about it if you were to find a common denominator. If this were just x plus 1, okay, so we have x plus 1 and x plus 1. The problem with doing that, as having both of these as x plus 1, is that the common denominator would just be x plus 1. But this isn't x plus 1 here. This is x plus 1 squared. So when we do this, we have to think of the denominators, okay? So we need a common denominator of x plus 1 squared. The only way to get that is if one of our denominators is x plus 1 squared. Okay, so you might say, okay, well, x plus 1 squared I could write as x plus 1 times x plus 1, but we need a common denominator of x plus 1 squared, and if we have x plus 1 and x plus 1 here too, then that won't happen. Our common denominator is at just x plus 1. Okay, but both of these are considered linear, so we would have an a and a b, so this is not considered quadratic. You're only looking at what's inside the parentheses. So we need the common denominator. To be x plus 1 squared. Which is why we divide it up this way. Okay. But then when we figure out the numerators, we're looking only at what's inside the parentheses. Inside the parentheses is something that's linear. That's why we have a b here. Let's take another example. Let's say that we have 2x plus 1 over x cubed times x squared plus 2 squared. Okay. So we're looking at the multiplicities with the degree, okay? That's what we're looking at. The degree here is 5. I don't really want to say that. That's not really the degree of the polynomial down here. We're looking at the multiplicities. So we have 3 and we have 2. That means that we're going to have 5 fractions. So I'll show you how that works. So we're adding them. You're always adding them until you find the constants. Okay. The x cubed, well, you could have an x. You could have an x squared, but you need an x cubed in order for the common denominator to be x cubed. So notice you keep going up until you reach this power. So you have denominators of each power of x until you reach 3. Again, it has to do with the fact that your common denominator would have an x cubed in it, okay? So we have x squared, x cubed, and then we're going to do the same thing with the x squared plus 2. You have an x squared plus 2 to the first and an x squared plus 2 to the second. So you start at 1 and you keep going up until you reach that power. And then you look inside the parentheses to see, is it linear or quadratic? So x is linear, so it's a. this, think of it as in parentheses, x squared. X is linear, so you have a b. X is linear, so you have a c. Okay? So the only way that you're ever going to have anything potentially quadratic is if you're adding or subtracting to your x to some power. Okay? So this you're adding to, so this is going to be a dx plus e, and this is going to be an fx plus g. So here, this is still linear. You're not adding or subtracting anything from x squared. Let's do one more example. Okay. Let's say that we have 3x cubed plus 7x squared minus 1. Numerator is kind of irrelevant. Let's say that we have an x to the 4th times x squared plus 6 times x squared plus x plus 1, and we'll cube that. So let's look at how many fractions we have. Well, here's an x to the 4th. We're going to have a fraction for every power of x, not x to the 0, because x to the 0 is just 1, so that wouldn't do anything. We're going to have a fraction for every power of x up to 4. So there are going to be 4 for this one. Here, notice there is no exponent, so there's only going to be 1 for the x squared plus 6. And here, this is a 3, so that tells us there are going to be 3 for this. Now, notice x squared plus x plus 1, not factorable, okay? And actually, I'm going to add in 1 extra here, just because I want you to see 1 extra thing. So let's add in a 2x plus 1 squared, just for the fun of it. Okay. So that means that we now have 4 plus 1 plus 3 plus 2 fractions. Okay, so that's going to be 10 fractions. So we're going to write this all out. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So let's just do the bottoms first. So we have the x to the 4th, which means that we're going to have an x to the 1st, and an x to the 2nd, and an x to the 3rd, and an x to the 4th. That takes care of the x to the 4th. Okay, in a different color, let's do the ones that are associated with x squared plus 6. So there's actually only one, because x squared plus 6 is just raised to the 1st power. Then we're going to do all of the ones associated with x squared plus x plus 1. Well, we have 3 of those, because we have x squared plus x plus 1 to the 1st, x squared plus x plus 1 to the 2nd, and x squared plus x plus 1 to the 3rd. Okay, and finally the last one, the 2x plus 1 squared. Well, we have a 2x plus 1 to the 1st, and then we have a 2x plus 1 squared. Okay, so now we just have our numerators. So our numerators are nice and simple. It's either going to be in the form of a constant or it's going to be in the form dx plus e or ax plus b. So all of the x's are linear, right? Because the power is irrelevant here. We're ignoring the power on the outside. So x, x squared, x cubed, and x to the 4th all get just letters. A, B, C, and D. Now we look at this x squared plus 6. This x squared plus 6 is quadratic. So it's in the form ex plus f. We're just going in the order of the alphabet. It doesn't matter that much. You just don't want to repeat letters. Okay, so if you skip a letter, don't worry about it. Now we're going to look at these. So x squared plus x plus 1, that's quadratic. So this is going to be gx plus h, ix plus j, and kx plus l. Now we're going to look at the 2x plus 1. So 2x plus 1 is linear. So we have m here. And then here again, 2x plus 1 is linear. This square is on the outside. It's irrelevant. So we have m plus n. Okay, so one quick thing. We're not going to do any examples of these. I just want to tell you what to do. So for improper fractions, so the thing is that you can't do partial fraction decomposition on improper fractions. So what that means is if you remember, when you're dividing, okay, you have your dividend over your divisor. Now you can't do anything with this if it's a proper fraction, okay? Right? 3 over 4, you can't divide. Otherwise, your dividend over your divisor is going to equal your quotient plus your remainder over your divisor. So if you have an improper fraction, you're going to divide, and then you're going to do a partial fraction decomposition on this. So you have to do your log division first. Then everything is the same. It's just that the fraction that you're using to do that partial fraction decomposition is the remainder over the divisor. Because that has to be proper. Okay? If you remember, we say we know we're done when the degree of the divisor is greater than the degree of the remainder. That's how we know when we're done with division. Okay, so we do long division first. It's usually going to be long division. Okay, you would do your long division first, and then you take your remainder over your divisor, and you do partial fraction decomposition on that. Okay, and that's it for partial fraction decomposition. The next thing that we're going to look at is rational functions. So we've been looking at rational expressions. We're going to be looking at rational functions and what they look like on a graph, and then that'll be it.